Okay, let's get started today. So hope you had a good weekend and relaxing. Perhaps also got some work done. So we are headed into two-dimensional arrays and vectors of vectors today, which are two sides of the same coin. And the agenda for today, we actually have some unfinished business with vectors. So we'll actually go back a couple lectures and finish up a couple of things with vectors that were in Dr. Planck's notes. And then we're going to just quickly review 2D arrays, which you were first exposed to in CS 102, but I know not extensively. And we'll have you do a short exercise from the textbook with two-dimensional arrays. Then we'll segue to vectors, or a vector of vectors, which is a way to do 2D arrays with vectors. As part of that, you'll be introduced to a new construct called the type def, which allows us to create new types. And then finally, we're going to talk a little bit about Lab 2, especially because you can solve it, at least the last problem, using a vector of vectors. So to start, let's go back to the August 25th lecture. And there was a couple things that I wanted to point out at the end of that lecture. Remember that the course, one of the things about this course is that we want you to be able to program efficiently, not just kind of brute force, but to be able to consider the consequences of your design choices. A big thing when you get out into the real world and you're designing solutions to problems, you want to consider alternative design choices. And some design choices are better than others. So here's a program where what we're doing, there's a Unix utility called tail that will print the last few lines in a file. So for example, if I go, let's see, to play, and let's look at, I'll cat out line counter.cpp. So there's the entire file. If I just look at the bottom, if I say tail, say 10, well, let's just start with tail of line counter.cpp. It prints the last 10 lines. Okay, and you could actually change that. Okay, there we printed the last 5 lines. So first of all, can anyone tell me what these things constitute? What are they called? Command line arguments. Very good. So those are arguments that tail is taking and is using. So in the first version, it's simply taking this file and it's printing the last 10 lines since that's the default. Here, we're giving it a second argument which says only print the last 5 lines. So tail is a Unix command that prints the last X number of lines in the file, where X is a command line argument. By default, it prints 10. So here's a very simple implementation of such a program. Now this one doesn't use command line arguments, it's reading from standard in. But a vector is a very good way of handling tail, because you need to basically, you don't know until the very end of the file that you've reached the end of the file. So you need some way of storing lines so that when you're at the end of the file, you can then go back and print the last 10. So for example, if my file were, say, Brad, Sue, Xavier, Zirkus, and Mike, and let's just say that tail prints 3, the last 3 lines rather than 10. Well, if I read them in and store them in a vector, then at the end I can simply go back 3 spots and start printing from 3 back. And a vector is good because I don't know how big the file is, so I can't use an array, so I need to use a vector. So I've created a vector of strings, and then I read a line at a time into S, and I simply push that line back onto the vector. Then when I'm done, I find the index of the first line I should print, and that should be 10 lines from the end of the file. So I go back 10 lines. Now, I need to worry about files that have fewer than 10 lines. If the file has only 6 lines, what's the problem? What will I first of all be if it has 6 lines? -4. And what's the problem? Is there a problem?
That's not an index in the vector.
That's not a valid index. So if the index is negative, it means the file did not have 10 lines. It was shorter than 10 lines. So we call that an edge case or a boundary case. In that case, we want to reset I to 0 because we're printing all the lines in the file. And the first line would start, obviously, at I equals 0. So that's what this check right here does, is it makes sure that I is not less than 0. It handles the case where there are fewer than 10 lines in the file. And now we simply start from where I was. While I is less than lines.size, we increment I and we print out that particular line. Notice we didn't have to have anything in the first spot. That's optional. Okay, in this case, we'd already done our initialization of I, and there was no further initialization to be performed. So we left that statement blank. Okay, you sometimes see that. Okay. You sometimes see this blank as well, in which case that expression defaults to true, and you're in infinite loop. You pretty much never see the increment statement empty because the point of using a for loop is to increment the loop variable in some way. If you're going to leave that field empty, you might as well use a while loop because you're actually changing your loop condition or variable in the body of the loop. You might as well use a while loop. So typically, the last field, which is the increment field, is never going to be blank for a for loop. Okay, so this works. If you run it, it will print the last 10 lines of the file, or if the file has fewer than 10 lines, it will print all the lines in the file. But if you stop to think about what's happening, you'll realize that there's an inefficiency here. And that is, let's say the file is very large. It contains 100 million lines. Okay, how big is our vector going to be when we're done? 100 million lines. That's a lot of storage because each line, let's say the line, each line has an average of 50 characters. That's 5 gigabytes. Okay? Not even clear that all of that would fit in main memory because we share main memory with other programs. So we might actually be forced to source some of that out on disk, and it's a lot slower to access stuff that's been pushed out onto the disk than it is in main memory. So this is not the most efficient solution, and we might think about, is there a way to reduce the storage requirements of this program? Okay, so that's where it's helpful to think back to what are the constraints on this program. Well, the constraints are we want to print out only the last 10 lines. So maybe if we could figure out a way to always store only the last 10 lines of the program or of the file, that would be a lot more efficient. So it's kind of like we're keeping a moving window. So if we have a big file, okay, and so far we've read this amount, what we'd kind of like to do is only store the last, so if we've read up to I, we'd only like to store the last 10 lines. So somehow, every time we read a new line, we'd like to add that, but then we'd also like to get rid of that so-called 11th line. And if we can do that, then we'd only have to store 10 lines at a time, which is a lot more efficient, a lot less memory involved. In fact, no matter how big the file is, we guarantee ourselves we don't run out of memory, which is a problem with the first solution with really big files. Okay? So, here is a second solution. And your first idea could be, well, I can delete from the front of a vector, and I can add to the end of the vector. So what I'll do is I will simply add a line via pushback to the front, and then I will delete a line, add a line to the back, okay, like that, and then delete a line from the front. Okay. Well, that's inefficient. The reason it's inefficient is that when you delete from the front of a vector, you have to move each line down one. It doesn't actually empty out this first entry. Instead, what it does is it moves the second entry down to the 0th entry. It moves the entry at 2 down to 1, and so on. So it moves all 10 lines in the vector, and that's very inefficient. So a more efficient approach is to allow the vector to fill up. So we're going to have a vector of size 10. But eventually it's going to get full. Okay, so we start reading in lines. Okay, so let's say it's Brad, Charlie, Sue, Nancy, blah, 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 Carol. And now I read in my 11th line. Okay, so let's say I read in Smiley, it's my 11th line. What I'm going to do is I'm going to come back, well, B is now the line to be deleted. So I'm going to roll around to the front, and I'm going to delete B and replace it with Smiley. Okay, and now I'm just going to continue. The next one I'm going to erase is line 1. If that is, say, Mike, I'll put it there. So I'm rolling around to the front of the vector, and simply keep doing that as I read in lines. And then when I'm ready to print, well, I'm going to basically, if the next entry to read into is 2, which it is now, well, that's simply now the last line that I need, or the first line I need to print out. It's the last of the 10 lines. So if I now printed out the last 10 lines in the file, I would start at S. Okay, now we'll still have to worry about the case where there's fewer than 10 lines in the file. But let's just see what's happening first. So I start out, same way, I'm reading a line. And if the line number is less than 10, so LN is an abbreviation for line number, I still do pushback. But if the line number is greater than 10, I'm doing my wraparound. And we use the mod operator, which is the percent sign, to do our wraparound. So for example, when line number becomes 10, which is the 11th line in the file, 10 mod 10 is 0, and we'll end up writing S into entry 0 of our vector. Okay, and then we increment, after we've read the line, we increment ln. Okay, so when we're done, we do the same thing we did before. We know how many line numbers there were. And we subtract 10 from the line number. And as before, if I is less than 0, we know there were fewer than 10 lines in the file, so we set I to be equal to 0. And now we simply iterate through again, except that now we mod I by 10 in order to figure out where we're printing out. Okay, so it works well. In our previous example, I ended up reading 12 lines. Okay, I end it right here. So when I was done, ln was equal to 12. So when I subtract it, when I did this statement, I got set to 2, which is exactly where I wanted to start my printing. And 2 mod 10 was 2. And then we kept incrementing. So eventually, when we got up to I equals to 10, we were modding I by 10, so we ended up naturally wrapping around to 0, which is what we wanted to do. So this is a very efficient, elegant solution to our tail problem. We have used a vector that is only, or is at most, 10 entries. We avoided the inefficiency trap of deleting from the front of the vector. So we've saved memory, saved ourselves from falling into the trap of deleting from the front of the vector, and we have a very nice solution. And no matter how large the file is, we will not run out of memory. Okay, so this is a good example of thinking about a problem and not necessarily going with the first obvious solution that comes to mind. Because the first obvious solution doesn't work well with large files. Okay, it wastes memory. Memory allocation also is not free. Every time we call pushback, there is overhead associated with doing extra allocation. And one of you asked after one of the lectures, well, what happens when a vector quote becomes full? Because a vector only has so much room. Well, what happens is that when you allocate a vector, even if it's initially of size 0, it actually allocates some memory for the vector. Okay, maybe it gives it, say, 4 entries. Then pushback is simply putting things into these entries, and when it hits the next one, it says, oh, I'm out of memory, and it goes and asks the memory allocator to give it a bigger chunk of memory. Typically, it doubles the size of the vector, so now it would go up to size 8, or 8 elements, and it would copy these elements down to the new vector, and then when it was done, it would hand the old vector back to the memory allocator. So this one would be handed back to the memory allocator. Well, that is a slow process. That process of asking the memory allocator for twice as much memory, copying the old vector to the new vector, deleting the old vector, that all happens without you seeing it. It happens automatically, but it takes time and it's inefficient. So you want to avoid this as much as possible. So that's why you need to be aware of using up too much memory in your programs. Why you need to be aware of things like the danger of deleting from the front of the vector. It's an inefficient operation. And you often have to think beyond just the first obvious solution or the second obvious solution to possibly a third solution. Okay, and this will come up for you very often. The more you get into your courses, the more freedom you'll be given in labs to do your own design. You'll be asked to consider alternative design choices and come up with an efficient one. And you'll be graded on how efficient your ones are. Now, at this point, the labs are still sufficiently simple that often there's only one good way to do it. But that won't always be the case. So questions about any of this? Yes?
What's the advantage of using a vector on this particular problem? Since we had a big size of 10, can we have used an array as well?
Yes. So that's an excellent question. The question was, what is the advantage of using the vector here? Because we knew that we had 10. Could we use an array? Answer is absolutely. So in fact, the more efficient solution here would have been to use an array because we knew in advance how big it was. Now, if we had modified this so that it took a command line argument, now we might have to go back to using a vector because we don't know at the time the program starts how big the array is. Okay, so it works here because we know it's 10, but add that command line argument, probably back to using a vector. Okay, I'll say that with a caveat. Later on, we'll see how you can actually, at runtime, allocate arrays, but we're not there yet. We don't have the tools. Other questions? Okay. Now, at the end of his notes, Dr. Planck has this little for loop. So up here, he was saying if I equal line size minus 10, if I is less than 0, I equals 0, and he wasn't doing anything in the for. But he could have actually put that all into the initialization statement of the for loop. He could have said lines.size minus 10 less than 0. You may not have seen this so-called tertiary form of an if-then-else, but what this is a so-called tertiary conditional. Okay, it's tertiary because it has three parts. It has a condition, then the question mark, the true expression, a colon, and then the false expression. And a tertiary conditional returns a value, unlike a if statement, which executes statements. So returns a value. So you can't put statements in the true and false branch. You put expressions, and you can have only one expression. So here, if lines dot size minus 10 is less than 0, we have this tertiary conditional return 0. Otherwise, we have it return lines dot size minus 10. Okay? And when he runs it, it doesn't work properly. Okay? It turns out that for some reason, it thinks that this condition right here always evaluates to true. No matter what the size is, okay, it always evaluates to false, my bad. Always evaluates to false. No matter what, it always evaluates to false. And it always returns lines.size minus 10. Now, if we try to compile this, we see what happens. So, see if we have tail here. Okay, we don't, so let me copy this. Have to erase this. Okay, so I'm going to copy this in here. Okay, and what can I use to make this nicely indented? GG equal G. Very good. Okay, now I'm going to change. I'm going to get rid of these two statements. And actually probably get rid of the third two. Going to bring this one back in. Okay, so I just made it his all-in-one statement, and we'll try to compile this. Okay, and we get a warning. Comparison of unsigned expression less than 0 is always false. Okay, you're looking at it and thinking, how is that possible? That can't always be false. Okay, well, here's what's going on. I don't know whether in 130 or not you heard of a type called unsigned int. Did you or not? Okay. Unsigned ints are integers with no sign, hence always considered positive. The advantage of an unsigned int is what, other than that you know it's positive? There's another advantage to an unsigned int. Yes, Ryan?
Aren't they larger than signed integers?
They are larger. You can get 2 to the 32nd minus 1 with an unsigned integer because you no longer need the sign bit. Whereas with signed integers, you only get 2 to the 31st minus 1 because you have one bit that goes to the sign bit. So unsigned integers can be twice as big as normal integers. Okay? Well, they also, as I said, we know that they're always positive. So when you call lines.size, what do we know about the size of an array or a vector? Always positive. So the C++ developers decided that the return type for the size function would actually be an unsigned int. Okay? So line.size returns an unsigned int. Well, it doesn't matter what arithmetic expression you do with an unsigned int, C++'s compiler just assumes that since you're doing arithmetic with an unsigned int, you wouldn't be so dumb as to make the result negative. Because after all, we're doing with an unsigned int. You must expect the expression to be positive. So the compiler makes the assumption that this entire expression is going to evaluate to a positive number. Okay? And therefore, since it evaluates to a positive number, it is silly to ask if it's less than 0. It can't possibly be less than 0. So C++ says I'm going to optimize it. Since I know the result is less than 0, I know at compile time that this expression is false. And therefore, I'm never going to evaluate it at runtime. It's a waste of time. I'm simply always going to return line size minus 10. I'm always going to set I to be line size minus 10. So, of course, when the file is less than 10 lines long, I ends up being negative and things fail. So his point here was you have to be very careful when you're using built-in functions. You need to know what the return types are, because sometimes they can inadvertently trip you up. Now, fortunately, my compiler generated a warning, and I was able to see what the issue was. But when he compiled it, his compiler did not issue a warning, and it just didn't work. And it was really odd. It took him a little while to figure out what was going on. Okay, so I guess the takeaway message from this one is that arithmetic involving unsigned ints is always assumed to return a positive value. And you should be wary about doing a computation with an unsigned int that could yield a negative value.
Is there any way to get around this error?
Nope. The reason there's no way, well, there's no way to force the compiler to drop its assumption. It turns out that the compiler writer built this assumption in, and they're allowed to. Okay? There is a workaround, which is you can't do it this way. You have to instead revert back to the way he did it there. Okay? So yes, there's a workaround, but not the C. You can't force the C++ compiler to assume that you could get a negative number. You have to change your behavior. You can't change the compiler's behavior in this case. Sometimes there's flags to the compiler, but in this case there's no flag I'm aware of that will change its behavior. And believe me, there's been some other occasions too where I felt the compiler made an unwarranted assumption and I can't get around it, and it really ticks me off. Okay, I think this is an unwarranted assumption. Okay, it's clear that there are cases where it is valid to have the unsigned int in a computation that could result in a negative number. So I think this is an unwarranted assumption on the compiler's part, but the compiler wins. Okay, it is the final say on the matter. Other questions? Okay, so that finishes with the first part, which is our business with vectors. So let's move on to two-dimensional arrays. So they're a natural extension of vectors. And in the textbook for today, it was relatively light reading. You had only section 5.12. Okay, so you were introduced to two-dimensional arrays when you were in 102. They're simply tables. Okay, so conceptually, they're a table with some number of rows and some number of columns. So in this case, we have an array with 2 rows and 3 columns, and you access it with the row first is always the first index, and the column is always the second index. Okay, so conceptually, a two-dimensional array looks like a table. That's how you think about it. So rows, and we use zero-based indexing as before. Okay, so if we execute each one, you see the first one goes into 0, 0, then 77 into 1, 1, and 99 into 1, 2. I know that's kind of fast. Hopefully you did it before you came to class today. Now, it is important that you also understand how things actually get stored in the computer, because that will help you with efficiency. So in the actual computer, it is stored actually as a linear array, in this case with 6 entries. And it is stored in what we call row major order, which means that the first 3 entries here are row 0, and the second 3 entries are row 1. So the entries are stored contiguously by rows. It is rare to see things stored in what is called column major order, which would have meant that the 2 elements of column 0 would be stored. So if it was column major, it would go 0, 0, 1, 0, then 0, 1, 1, 1, then 0, 2, 1, 2. So it would have been stored by columns. But that's not how pretty much any modern language works. Pretty much all modern languages use row major order. Okay? So when the compiler sees a expression like 1, 1, it actually kind of converts it to a computation that looks like 1 times number of columns plus column. So in this case, it gets 1 times there's 3 columns plus 1 is equal to 4, and it would access the entry at location 4, which as you can see is really 1, 1. Okay? So under the covers, the compiler is actually flattening your two-dimensional array into a one-dimensional array, and it's doing a computation like the one you see here. So it's really row times number of columns plus column. Now you won't do that, but you should understand how this two-dimensional array is actually laid out in memory. In part because in 130, did you learn about caches? Cache memory? Yes, sir. Okay. So cache memory is a lot faster than RAM, right? And one way we take advantage of cache memory is if we can load contiguous portions of memory into the cache in expectation of some operation. Well, it helps to know whether an array is laid out in row major order or column major order, because we want to exploit that when we write a program. It is more efficient to be able to walk through this array so that you access contiguous elements. That's more efficient for the cache. Okay? So it helps to know that in this case we should write our for loops so that the row is the outer index and the column is the inner index. It's much more efficient to write your loops this way than to put the column as the outer loop. And the reason is because we'll start with row equals 0. And then with row equals 0, we'll go through these 3 entries. Then we increment row to 1. And now we'll go through these 3 entries, and we're going through that 2-dimensional array by accessing the elements contiguously in memory. That is much faster, it turns out, than reversing the order of those for loops. So while it may look on the surface as though it shouldn't matter in which order I write those for loops, it in fact is very important in which order I write those for loops, because it will be much faster if I walk through the 2-dimensional array in what we call row major order. Okay. So the takeaway lesson here is that with 2-dimensional arrays, you iterate the rows as the outer loop and iterate through the columns as the inner loop. So iterate through 2D arrays such that, or not such that, iterate through 2-dimensional arrays using rows as outer loop and columns as inner loop. Okay, that's the takeaway lesson for row major order. If this was column major order, then it would be reversed, and you would iterate using columns as your outer loops and rows as your inner loop. Okay, so questions about that? Okay, so just to warm you up, there's a challenge activity here. If you have your computers, please turn your attention to the challenge activity. If not, try to do it on paper and pencil. So we want to find, we're actually have this program called Miles Tracker, where we have some number of rows and some number of columns. And the idea is that we're storing the distance between cities. So we might, 0, 1 might be the distance from Boston to Chicago. 0, 2 might be the distance from Boston to LA. So we want to find among all of our routes the shortest and the largest. So we need to go through all the entries in our 2-dimensional array and find the smallest entry and the largest entry. So you can see what they've given you. There you can see line 18, your solution goes here. I'm going to give you about 5 minutes to write this program. Feel free to work with a neighbor. This isn't an activity that we're grading. I'll go over it at about 10:30, the answer. And if you have a question, raise your hand. Sure we're recording. Yep. Okay, so here's the solution. The first thing they told you to do was to assign the first element in Miles Tracker before the loop. So the first element is 0, 0. Okay, that's the first element. Now, the reason you do that is you can't be guaranteed that the data is going to fall in any given range. So they had it set to minus 99 and minus 99, and you might think, okay, I'll leave it there. But some of their test data, I can't actually run it because I don't have my, no solution provided. But there it is. If you see it on your own, they used some test data that was outside the range of minus 99. I believe there was a minus 173 in one of the test data sets. So you can't, when you aren't assured that data falls in a certain range and you're trying to find a minimum and a maximum, a good rule of thumb is to simply initialize your min and max to the first element in the data. This is what we did here. Now you'll notice we iterate through the array by using rows first and columns second. We didn't assume that we didn't hard code 2 because they changed the rows and column dimensions on us, so they wanted us to use the constants. They use plus plus I. I prefer the postscript way of I plus plus, but no matter. So then the two comparisons, if the current entry is less than min miles, update min miles. If the current data entry is greater than max miles, update max miles. So a fairly simple thing. Now, I have one beef with their solution. Okay, and my beef with their solution is that the two cases are mutually exclusive. It can't both yield a new minimum and a new maximum. That is impossible. Therefore, you should put an else here. Because if the first if succeeded, it is impossible for the second if to succeed, and therefore it is an irrelevant comparison in that case. So if miles tracker is less than min miles, it is impossible for it to also be greater than max miles. Therefore, if the first if succeeds, you should never perform the second comparison. So I think it is better to put an else if there. Okay, so these are things you need to get comfortable and familiar with. It is part of learning how to become an efficient programmer. Small things like these add up in the long run. Okay, so try to use an else if there, even though both ways are correct. Yes?
It initializes the I and J in the given part of this, like the part that it gives us of the program. But then when I didn't reinitialize them inside the for loops, is that just this program? Like it didn't work.
Probably because they changed it so that they probably went ahead and set I and J to some bad values. Why?
They initialized them to 0.
I know.
Okay.
So technically, you should not have had to actually set them to 0 in the loop.
Okay.
Okay? They probably, behind the scenes, just like behind the scenes they changed num rows and num cols on you, they probably changed. They should never have set I to 0 and J to 0. It's just bad, okay? So whoever wrote this problem, that was bad form, okay? There is an art to writing problems well, okay? I used to do it. My dad was a textbook author, and I used to write some of the instructor manuals for him, and he used to be ruthless, and he would say, this is a bad question, and explain to me why. They should not have set I to 0 and J to 0 if they were then going to set them to something else behind your back. Okay? But that's what happened. Yes, you should not. Given that they set I to 0 and J to 0, you should not have had to do that. Of course, given that they set num rows and num columns to 2, technically you should have been able to hard code a 2 as well. But you should never do that. Okay. Other questions? Good question. Other questions? Yes. Pardon?
Where the J is second initialized again in the for loop.
Yes.
Isn't that so whenever you go back to the columns again, it goes back to
So yes, actually that's a good point. Is that he's got a good point. So this one you had to have because this one was unnecessary, but this one was necessary because every time you increment the row, you have to reset the column to 0. So it was necessary actually to set j equal to 0 each time. Other questions? Okay, so let's move on to vector of vectors, which is how you do two-dimensional arrays with vectors. Okay, so how do we do that? Here is one vector, and then inside of it we have a vector of events. So this is called a vector of vectors because the type of value that the outer vector is storing is a vector of ints. So the idea is here is our outer vector, and each entry in the outer vector is itself a vector of ints. Okay? And you can access the elements once they're set. You can access them just like you do a two-dimensional array. So you would be allowed, after having set values, to say things like data 1, 2. However, you're just like with the vector, before the value or entry is created, you can't do that. So we're going to have to use pushback and resize in order to actually create dimensions. Okay? So when this data is created, it doesn't look like the nice thing that I've drawn here. When it's created, it actually has 0 entries, and each of its, so it has 0 entries. When it starts, it's nothing. When data starts, it's nothing. Okay? Now, the first thing we might do is say data.resize 5. And now we would have a 5-element vector, but each of its individual vectors would still be of size 0. So that's not enough. All we've done here is resize the, we've said this is how many rows we have. But we haven't done anything about the columns. Okay, and it turns out that we have to individually change the columns either by, for each one doing a resize. So let's say we wanted a 5 by 3 vector. We would now have to say for, say r equals 0, r less than 5, r plus plus, you'd have to say data r dot resize 3. And that would go through, and for each row, it would make the vector in that row have 3 elements. So you have to individually go through each row and resize the vector. So this would give us a 5 by 3 vector of vectors. Okay? Now, this is not normally how you would actually set up a vector of vectors because you might not know in advance how many columns you have. So you might very well know the number of rows but not the number of columns, or you might know neither. So I'm going to go through each example. I'm going to start actually with where you know both the rows and the columns. And I'm going to illustrate it using Lab 2, which is what you're working on this week. Okay, so those of you who have not yet looked at it, shame on you, but I know many of you haven't. You're dealing with PGM files, which you should have probably dealt with in 102. Did you? Was there a lab with PGM files in 102? Yes, probably, because many of you took it the year I was teaching it last fall. So you have these PGM files, which are ways of representing images. And if you remember, a PGM file starts with the string P2, which just indicates the format. There's several different formats for PGM files, P1, P2, P3, P4, so different standards. This is saying it's in the P2 format. The next two data values give the number of columns and the number of rows, which is irritating because the data is actually presented in row form. So why they made it column and then row, but that is what it is. So this is columns and this is rows. So you know in advance how many columns and rows you are. This is actually just saying what is the maximum value, pixel value, 255, and you will ignore it in your data. And then the remaining data are your pixel values, which go from 0 to 255. And they give the intensity on a grayscale. So if I remember correctly, 0 is white and 255 is black, I believe. Or is it the opposite? Yep, 0 is black, 255 is white, sorry. Again, counterintuitive. But 0 is black, 255 is white, anything in between is some gradation of gray. Okay, so you obviously just get black and white images with a PGM file. So what you'll be doing in lab 2 is reading in one of these files, obviously doing some error checking, and you're doing different operations on them. Initially, you're just printing out some information about them. So the first one is printing some information about the file. The second one, you're just creating your own white PGM file. But then you start doing some more interesting things. You negate the image, so everything that's black becomes white. Everything that's white becomes black. The fourth one flips it. So this is, for those of you who like the 70s show, and yes, it is a show that's not been on for a while, but this is a show that Dr. Planck liked. So there's it before he's flipped, and here is red after he's been flipped. So that's called a horizontal flip. And here he's been flipped on his head. So those are 5 programs you'll write for lab 2. Now, listen carefully. The first 4 programs do not require a vector of vectors, and you will be penalized if you use a vector of vectors for the first 4 programs. So programs, in fact, programs 1 through 3 require no vector. Program 4, which is H-flip, requires a 1-dimensional vector. Program 5, which is V-flip, is the only one where it requires a 2D vector. Now, you could do program 5 with a 1D vector, and the instructions tell you how. However, I would suggest you use a 2D vector or a vector of vectors. A 2D vector is a vector of vectors for the V-flip because it's simply easier to do that. So it's easier to read the entire file. And how do you think you do V-flip? What do you do with row 0 and the last row? You swap them. So you swap the 0th row with the last row, then you swap row 1 with the second to last row. It's just easier if you've set it up as a 2D vector. Yes?
Create an array, read the values out of this column backwards, and just override them like that.
Can you do what? Create an array?
Yeah, create an array, since you've already told how many rows there are. Just break the
Okay, except we haven't, the answer is yes, except we haven't told you how to create a dynamic array yet. This would require the use of pointers, which we haven't gotten to. So, okay, we're not going to use the post C11 standard. So the post C11 plus 11 standard would allow you to do it, but you can't. So how do you propose to create this array? At compile time, I have to declare this array. I'll call it picture. And I don't know at compile time how many rows and how many columns. It's only when I read that information at runtime. I see. So, okay. Dr. Plank doesn't let you do that. Dr. Plank and good programming style is you declare all your variables at the top, and then you read stuff after that. Not really. And then you have to use, we'll get in, come up afterwards, okay? There's not an easy way to do it. There are ways, but not ways that we have told you yet, okay? And it requires some additional instruction. So don't use an array, okay? Just don't use a vector, because TAs expect you to use one, okay? If you start using stuff that we haven't talked about, they're going to assume you pulled it off the internet and that you plagiarized, okay? So please, talk to me after class, okay? Yes?
So for the lab, are the only error cases that we would have to deal with are the stuff in GM info?
Are the stuff what?
The error cases that are listed in PGM info, those are the only ones that we have to worry about?
There's going to be some other issues. Believe he's going to give you some corrupted data. So it's not just that the number of rows may be not a string, or that the rows might not be an integer. It might be the case that one of the pixels isn't an integer. It might be that he doesn't actually give you as many pixels as he claimed he would. So there's some other error conditions. I just told you 2 of them, so yes.
Do we have to check for all those error conditions in every program that we do, or do we just do that?
If the grade scripts, if he does with the grade scripts, then yes. So my answer to that is just copy and paste. Okay? Copy and paste. Yes?
Like, you said we'd be penalized if we didn't do it like that. Like for program spawn and 3, we need to not use vectors.
Yes. Because it's inefficient to use a vector. There's no reason to use a vector. You don't have to store. You can write the program in a way that doesn't require you to use a vector. Okay, it's inefficient for programs 1 to 3 to use a vector because you can write them in a way that doesn't require you to use a vector. Okay, program 4, you can flip a row horizontally without knowing what any of the future rows are, which is why you only need a one-dimensional vector. You need to know to do HFlip. So to do HFlip, you need to know, you have to store the entire first row because you have to, at the end, take the first bits and flip them with the last bits. But to do HFlip, you can flip the first row without knowing what rows 2 through n are, right? So you only need to store one row at a time, which is why you only need a one-dimensional vector for program 4. Yes?
Would using like a single vector, or a 1D vector and then another 1D vector be counted the same thing as a 2D vector, single 2D vector?
Well, okay. When I talk about, yeah, you can use 2 1D vectors, although You shouldn't need to. You only need one 1D vector for program. For 5, what you really need to do is you're going to have to write it like this. Okay? Except you'll use type defs, which I'm probably not going to get to today, but I'll probably have the TAs go over it quickly in lab. But you'll write it instead like that. Okay, now, so let's say you have read in, so you'll have, let's say you're writing program 5, and you have read and verified that rows and columns are an int. Okay? And let's say I called my vector of vectors pick. So, I know how big it is. So there's two ways to handle this. I could simply say for, well, actually I can start by simply saying pick dot resize what? Rows, because the first thing I do is I set up however many rows I need. Now I want to read the data. So I'm going to read the data. I always start with my rows first. Okay, here's way 1 to do it. Okay, inside the loop, I say pick r dot resize what? Columns. So for that particular row, I resize it to that number of columns, and then I say for r equals 0, I'm sorry, c equals 0, c less than columns, c plus plus, and somehow I read, I could probably say, I forget whether we're using, I'm just going to say CN for the time being. It may well be you're using files. I forget whether you're reading from CN or from a file. But at any rate, you could say this, pick RC, because we've already set up that row. Okay, so that's one way. So this is way number 1. Way number 2 would be to say for, you still do the pick dot resize, but then you say for r equals 0, r less than rows, r plus plus. Then you say for c equals 0, c less than columns, c plus plus. You read into, I'll say pixel, and then you say pick r dot pushback pixel. Either way works. The reason it works either way is because in this case I know in advance how many pixels are in each column. So I can do 1 because I know in advance how many pixels are in the column. If I did not know in advance how many pixels were in the column, I'd have to use 2. Okay, so in 2, I'm simply reading the pixels one at a time and doing pushback. And since I execute the inner loop, how many times do I execute the inner loop? How many times? Number of columns. Therefore, I do number of columns pushback. And so at the end, I've created also a vector that has column pixels in it for that row. So either 1 or 2 both achieve the same ends. Which you use is up to you for this problem. It works. 1 works because you know in advance how many columns there are. 2 always works, regardless of whether you know in advance how many columns there are or not. Okay? So questions about that? So that's how you would fill up your picture vector for program 5, which is vflip, and then I'll leave it to you to figure out how to actually do the flipping, but you can do the flipping of the rows using the two-dimensional array operations you used earlier in class. Okay? So I'll have the TAs go over type defs tomorrow so that you understand them, and we'll reconvene. See you Thursday.